Well, before we get into 11.6, let's recap all of our series tests because they're starting to add up. And we're going to add the last two in 11.6, so that's exciting. What do we have so far? We first learned the geometric series test, and that one's nice. If you can identify it, we'll know immediately if it converges or diverges. Then there was the divergence test, and I noted that in the divergence test, the only thing that you can show is that a series diverges if you take the limit of the nth term and it does not equal 0, right? The third test that we learned was the telescoping series, and that one really feels different than other tests. Um, there's not a formula for it. You have to find the formula for the nth partial sum, and you use partial fractions to do that, and kind of the terms end up collapsing and canceling out. But okay, yeah, that was the telescoping series, and the process is what we call the test. All right, then we went on to the integral test, and the integral test is a beast, right? So you got to show these three conditions are true for f of x, that f of x is positive, continuous, and decreasing, and then that just shows you can apply the test at all, and you take the integral from the starting point of the series to infinity, and right, if the integral converges, then the series converges, and if it diverges, then the series diverges. All right, but a really nice consequence of the integral test is the p-series test. Feels a lot like geometric series test. We can just look at the p-value 1 over n to the p and know just from that if it converges or diverges. Then we learned the direct comparison test and the limit comparison test. I actually group these as one. Obviously, they're two different tests, but I just list this as number 6 because the way I present it and the way I think about it, I always begin attempting to do it by DCT, and if the logic doesn't work, or if it's backwards than what it should be, then I fall back on the LCT. That's the way I think of it. So what was it? Well, if you compare it to a new series, a simpler series, and it gets smaller, you want that new series to diverge so that the bigger one, the original, diverges. Or if you compare it to a new series and that new series is bigger, then you want that new series to converge so the smaller one converges. So that would be a DCT. But if it's ever doesn't work out the way you want, you're all set up for LCT. Okay, that's all I'll say about that. And finally, the last one that we learned was the alternating series test. We introduced alternating, where the terms alternate positive and negative. And it turns out if the terms alternate positive and negative, then it's much easier for a series to converge because they're always canceling out as you're adding them up. Um, and so there's a nice test for that, fairly simple. Um, and if I should have, we can only show converges here if it happens to be that one of the conditions, really the first condition in the alternating series test, fails. Then what's nice is even though the test is set up to only show converges, we would then immediately fall back. If that first limit does not equal 0, then we know that it actually diverges by the divergence test. So that's kind of like the backup plan. Okay, so there are the tests. Let's now get into 11.6. And it's actually got multiple parts here. So we learn, as promised, the last two tests. They're called the ratio and the root tests. But before we get to those, we need to develop this idea of absolute convergence. And that's the theorem, or what's leading to this theorem will lead to absolute convergence right here. Okay, so the theorem says if for n equals 1 to infinity, the absolute value of an, if that converges, then we know if we were to remove the absolute value, then that would converge as well. This it makes sense why this section would come right after alternating series, although we're generalizing it more here. So imagine you've got a series. If you were to take the absolute value of every term, originally, maybe some of your terms were positive, some were negative. Maybe they're alternating back and forth, but maybe not. Maybe just some were negative and some weren't, right? If you then make everything positive, it is a lot more difficult to converge. If some are positive, some are negative, when you're adding them up, they'll sort of cancel each other out a little bit. But if you make them all positive, then you're always adding and you're always going up, up, up. It's a lot more difficult to converge when you're always moving in the same direction as you add the terms. So we're going to say if in making them all positive, if that converges, then we know that removing the absolute value, it converges. This is the worst case scenario for a series, if you will. If you make everything go in the same direction, if that converges, well, certainly if some of them then are allowed to be negative, it will converge as well. Hopefully that makes sense. Okay, so because of this theorem, which we're not going to prove, we're going to define a couple of things. We're going to define absolute convergence, but we're also going to define this thing called conditional convergence. Okay, so here's the idea. If when you take the absolute value it converges, then we're going to say, sure, now that original converges, but we're going to give it an even stronger name than just converges. We're going to say it converges absolutely. And the name comes from because we took an absolute value, right? Even if you put this in the worst position possible, you make every term positive, it will still converge. It's like super convergent. And I like when I think of converges absolutely, I almost think of that like it's a super convergence. Absolutely. It converges absolutely, right? It's like this exclamation point. It really converges in under the worst position, the worst circumstances possible. Okay. When you take, let's say though, what happens on the other hand? Let's say, what if when you take the absolute value, it diverges, but removing the absolute value, like the original series, that converges. So if some of them are allowed to be negative, it converges. However, making them all positive, then it diverges. Then we're going to say the original, sorry, this is so blurry. We're going to say the original series converges conditionally. Where does that name come from? In the case where not just some of the terms are negative, but it kind of even more than that, it's like the right terms have to be negative. If you make the correct terms negative, then it will converge. But if those negatives are removed or rearranged, it might very well diverge, right? It's like at this critical point where if one or two things were changed or you know, who knows how many, it converges now, but if it was just tweaked just a little bitty bit, it would diverge. And certainly if you made everything positive, it would diverge, right? So we're going to say that converges under the right conditions. It converges conditionally. So now we're going to just kind of play around with this idea. And the question is going to be, does the series, we'll just do one of them, does it converge absolutely, conditionally, or does it diverge? Okay. So we're going to get a few questions, you know, like on your test or something. You might get, you know, one or two where it's asking now to go further, not simply converge or diverge, but converge absolutely, converge conditionally, or diverge. I should probably be really clear. Does it converge absolutely? Does it converge conditionally? Or does it simply diverge? Okay. And now this could, depending on how we approach it and how it works out, it might not be any more work. than the original converge or diverge scenario, or it could be twice as much work. So we'll just see what happens here in this one example. N equals 6 to infinity, and we're looking at negative 1 to the n power over the cube root of n minus 5. Uh, makes sense why we start at n equals 6, so we don't divide by 0, All right, anyway, does that converge absolutely, converge conditionally, or does it simply diverge, right? If it diverges, then that's just it. That's just it. There's no special name for that. It diverges, it diverges. Well, you might start by trying simply to show that maybe there's a couple different angles you could take. Maybe you speculate that this thing diverges. All right, then you might start with the original series just the way it is and look at that. And now any test goes, right? So who knows what test we might use. Or maybe you speculate that it's the other extreme, that this converges absolutely. That's the way I'm going to start it, just because that's the new idea, especially. Um, and I'm showing you quite a bit of work here. That's all right. So I'm going to begin by taking the absolute value of my, whatever name you get, the nth term, including the alternating piece. So I'm going to take the absolute value there of my nth term, and I'm going to simplify that, right? So the negative 1 to the n would simply become a positive 1. My denominator is always positive anyway, so that's the same. So in taking the absolute value, it just means now every term is made positive, so I've just got a positive 1 up there on the top. Okay, so now any test we could apply here. Whatever test we think might apply there, we're going to go for it, and we're going to see, after taking the absolute value, does it converge or diverge? Okay. If it converges, then we're done. We've converged absolutely. If this diverges, then we're not sure. We're going to have to look further. Okay, so anyway, taking the absolute value gets us here, and you kind of see where my thinking's going. I'm like, oh man, you know what? If this minus 5 was not there, then I could apply a p-series. So I'm going to get rid of the minus 5, okay? And then I got to think, well, what happened? Is the new series bigger, smaller? What symbol do I put in the middle? Well, let's see. If I remove the minus 5, I really add 5. So my denominator is bigger. That makes the whole thing smaller. Okay, so I'm going to do this. Denominator got bigger, so the whole thing's smaller. All right, so far so good. So then I'm going to rewrite that cube root here, and sorry it's so blurry, 1 over n to the 1/3. And I'm going to use a p-series there. Okay. Okay, well, let's see. If p equals 1/3, do you remember if that means it converges or diverges? It's easy to mix up. If p equals 1/3, that's less than or equal to 1. That diverges. We need that exponent to be bigger than 1 for it to converge. So this series right here, and I'm just using an arrow, that guy right there diverges by the p-series. Okay, so then let's look back. That is smaller than where we started. So what's true of this one? If the smaller one diverges, then the bigger one also diverges. Again, just a nice use of the arrows here. Let me pull this up. Hopefully it won't be, it'll get a little bit sharper on the screen. Okay, it's a little bit better. Okay, so that diverges. This one is bigger, so that diverges by DCT. I know what happens there. Okay, that's great. But let's see. What does that mean for the answer to the whole thing? So if taking the absolute value diverges, oh boy, you know what? We don't have an answer yet. So here's what I've written, just like not really a step so much as just the thinking. The original series that we're looking at, it might simply diverge or it might converge conditionally. It definitely does not converge absolutely, because when we took the absolute value, it diverged. So we know it does not converge absolutely. Had this worked to converge, we'd be done. We'd say it converges absolutely. But since it diverged, now we don't know. Maybe if we allow that numerator to alternate, maybe it converges then. Maybe it diverges no matter what. We got more work to do. No problem. So where do we go from here? Well, we're going to look at it without the absolute value, and you might say we're just looking at the series now. Okay. So look at the original series, and of course, if it converges, then we'd say it converges conditionally, or maybe it simply diverges. Well, what are we going to do with that? What test are we going to apply? And I'll give you a moment. Go through the list of tests that we named before we started the section. And yeah, it's got to be alternating series test because we got that alternating part. Okay, so we're going to use alternating series. And I wrote that, but you wouldn't necessarily have to put that on a page so long as you cite your test later. All right, so I'll identify the AN, the non-alternating part. And we'll check the first condition. This is just a good kind of recap of some of these tests anyway. We're going to take the limit of this thing as n goes to infinity, right? That's the first condition. It does go to 0. Check. Then we're going to see if the terms are decreasing, and I'm going to go about it in this style. So I'm going to check the oh, I have this written backwards the way I normally do it, huh? My mistake. So I've got the, oops, did it again. I've got the nth term. It's got to be greater than equal to the next highest term. Well, if I replace n with n plus 1, the next highest term, I'd be subtracting 4. Hopefully that makes sense. Replace n with n plus 1, n plus 1 minus 5. Okay. Is this really true? It's got to be true for n greater than or equal to 6. Well, I'm going to cross multiply and land right here. And again, I have everything reversed. There we go. Cross multiply. And I'm sure it's going to happen again. If I cube both sides, well, then I get this statement right here. Okay, and now if I subtract n, and yeah. Negative, right? -4 is greater than -5, so that one works. Check. So both conditions of the alternating series tests worked out. So that means that the original series here, if I can't quite fit it all on the screen. Oh my gosh. The original series does converge by alternating series test. Well, if that converges, but when we take the absolute value it diverges, then what do we say about the original series? It converges conditionally, under the condition that it's alternating, that half the terms are allowed to be negative. It will converges conditionally. And yeah, wow, I mean, how many different tests did we see? We saw P series, we saw DCT, we saw alternating series test, all within one problem. That's pretty impressive. Okay, we're going to stop here. We're going to get to the ratio test. Yeah, there it is, in the next video.